Okay, this is going to be the video for AP Statistics, Chapter 11, which is about randomness and simulations. So this is the first of 3 chapters that are in Unit 3. In Unit 1, chapters 3, 4, 5, and 6, we talked about how you can analyze the statistics from a sample of data, a single variable sample of data, how the values are distributed across the values of the variable, things like that. We also talked about the normal distribution and various other things as far as mean and median, how to get a typical measure, how to measure how widely dispersed or spread the data is, things like standard deviation, IQR, how to determine if things are outliers, etc. And then in Unit 2, we talked about bivariate data, where every data point had an X and a Y, right? And those two are linked together. So mainly that's about analyzing whether there's some sort of an association between those two numerical variables, right? So, so far, we've talked about how to analyze data that has already been collected, right? In Unit 3, we're going to talk about how do you collect the data. That's actually quite important. In fact, it's at least as important as the analysis that you do on the data afterwards, because it turns out that if you do a bad job of collecting the data, there's nothing you can do in the analysis to correct for that, right? If the data has biases in it or came from a sample that isn't representative of the population, then there's all kinds of problems, right? So we're going to study all that in Unit 3. And Unit 3 consists of 3 chapters, Chapter 11, 12, and 13. All right, so Chapter 11 is our first one. Let me go ahead and start presenting the notes here, and we'll take a look. So Chapter 7, or Chapter 11, is the first of the 3 chapters, and if you look at how we're looking at the different aspects of collecting data, let me just talk about the unit in general. There's 2 main ways that you can take a sample of a population that you're studying, and we're going to talk about sampling techniques in Chapter 12, actually. And then in Chapter 13, we're going to talk about the way we collect the data that's different if you're doing an observational study versus doing an experiment. And an experiment is more strictly controlled, and because it's more strictly controlled, that's the only way that you can use your data to establish a cause and effect relationship. So we'll talk about the differences between studies and experiments in Chapter 13. We'll talk about the data collection methods in Chapter 12 and the various biases that can result if we don't collect things correctly. We'll talk about different sampling techniques. But in Chapter 11, we're going to talk about simulations. So simulations are using randomness in some way to generate a fake set of data, but a data set which is representative of something in reality, right? And we use simulations to produce data to analyze when it's either unethical to collect data because it involves, you know, like something that's unethical to do to humans, medical experimentation or something like that, or it's too costly to collect the actual data, right? And all of these things, experiments, observational studies, and simulations depend upon using randomness. So we're first going to talk about randomness. So in Chapter 11, we're talking about just randomness, and we're talking about simulating data by using randomness to create a data set when it's too impractical or unethical to collect the data in a real way. And then in Chapter 12 and 13, we'll talk about collecting data from the real world. All right, so the first thing we do in Chapter 11 is a class activity. We would do this in the class, even in virtual mode. So I'm just going to walk you through what that activity is like, and then we will we'll let you kind of participate in this at home if you like. So I'm just presenting the entire screen because we're going to go back and forth between different things here. So the Federalist Papers activity has to do with analyzing the Federalist Papers. And the Federalist Papers are a series of 85 essays that supported ratification of the US Constitution. At the time that they were published, the identity of the authors was a secret that was only known to a few people. But over time, the authors were identified as Alexander Hamilton, James Madison, and John Jay. Right? The authorship of 73 of these essays is fairly certain, but there are 12 of them that are still somewhat in dispute. However, thanks in some part to statistical analysis, most scholars now believe that the 12 disputed essays were written by either Madison alone or in collaboration with Hamilton. Right? So there's actually several ways to use statistics to try to determine who wrote something if you're not sure. And one method is to estimate the average word length in the disputed text and compare it to the average word lengths of works where you know the author is known, right? Because people tend to write in certain styles. Some people write with longer words and shorter words, or just more colloquially or more formally. And so, there's various things you can measure. And one of the things is average word length. So we're going to look at at a Federalist paper, and we're going to calculate the average word length, okay? And this would be done in the context of usually trying to establish authorship. So at this point, usually in the class, I pass out a piece of paper or have someone on their phones look at a passage from the opening paragraph of Federalist paper number 51. This is one of the disputed essays. Okay, so here on the screen, this part down here is the wording, right? And what we want to do is figure out what's the average length of the words in this passage, right? But rather than look at all the words, because there's many, many, many words, we want to just take a sample of words and then figure out the average in the sample. And then we can assume that as long as that sample is representative of the words as a whole, then the average in the sample is going to be pretty close to the true average for the whole paragraph. Okay, so here's what I'd like you to do. You can look at the paragraph here on the screen, choose any 5 words that you want, okay, and then just like select the words, and then for your 5 words, count up how many letters there are in each word, and then take the average. So just add up all the letters and divide by 5 to get the average amount of letters per word. So you can pause the video and then take a look at this paragraph and do that now. Okay, so once we do that, we say, well, could we gather all the data from different people? Because we have everybody do that. And typically what I do is I have everybody then take a dot and come up and put it on a dot plot. And we can create a dot plot of the average that every person came up with. So I'm going to show you a picture. This is a picture of the dot plot that was done by a class. It wasn't one of my classes, but it was from the teacher who showed me this experiment in a summer workshop. And so each of these dots represents an average. So for example, this person here, this blue dot means this person had an average of about 5 words or letters per word. These people had about 6. These people had 8.5. These people had close to 10 letters per word, right? So this is the data that we collected, right? And we could ask a question, which is, let me go to the next screen. What would we estimate the average word length is from this dot plot? Well, if I look at this, I mean, basically, I need a number that's representative from this data set. And from Unit 1, we know that we could use the median or the mean, right? So this looks kind of skewed, so maybe I would use the median, right? The median appears to be, well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's about 23 pieces of data here. So if I go about 11 in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, somewhere in this range, about 8.5 is probably where the median is, the middle data point. So let's say 8.5. 8.5 is the average letters per word from the data, right? Now, how accurate do you think it is? Well, if we look at the dot plot, there was a lot of variation from person to person. When we take an average, when we take a sample of something, right, that means everybody's going to get a different sample, and therefore we're going to get variation. Okay, so that variation that occurs, it happens naturally, right? So a lot of variation here, unfortunately. Okay, so the next thing that we usually do is I say, you know what, rather than just let students choose the words, because you could choose any words you wanted, what if we tried to come up with a little bit more formal procedure for making the sample? Okay, we're still going to select 5 words, but then I give out another piece of paper, and the other paper has this on it right here, which is a listing of every single word in this entire paragraph has been numbered in order. Word number 1, word number 2, and so on, all the way up to word number 130. So there's 130 words in this paragraph, okay? And then what we do is we use some sort of a random process to get a truly random sample of the 5 letters, okay? Or the 5 words to select. So I'm going to show you a procedure you can use in your calculator to let your calculator generate random numbers. Okay, so if you have a TI-83 or 84, you can turn it on. And then the first thing you need to do is you need to seed the calculator. The calculator actually can't do anything random. It's programmed, right? But it has a whole long sequence of random numbers stored in its memory somewhere. And what you can do is you can jump to some random place in that list and then start picking random numbers from there. That way, if you do an experiment and your friend next to you has the same kind of calculator, right? If you start at different places in that long list of random digits, then you'll actually have numbers that are random between the two of you, right? So to seed your calculator's random variable, what you need to do is type in an integer, a long integer, like 467,257. Doesn't matter what it is, just start typing some numbers. Doesn't even matter how many numbers you put in here. And then we're going to store that in the random number seed. So what we do is we press the store key here, which is right above the on button. And then we go to math, and then over here to the probability submenu, PRB. And then where it says rand here, you just hit enter and then hit enter to store that in there. What that does is it moves to a random position in the internal number structure. Okay, and then if you want a number, like let's say that I want to pick one of these 130 words at random, then you can specify a minimum and maximum number. Actually, that should say a 1. We want to pick a number from 1 to 130. So if you go back to math and then probability, and then you go down here to random integer, you can select that and tell me, give me 5 numbers between 1 and 130. So I'm actually going to put 1 and then comma 130 and then comma 5, and then close the parentheses and run that, and it will display 5 numbers. Okay, now if you happen to get any duplicates in there, then just run it again until you don't have duplicates, right? So this means take word number 40 in the list. So I would look that up on this list here and go, all right, that was the word exterior, and so I would count up the number of letters in that word. And then I would now take the 24th word, which on this chart is down, and count up the number of letters and do the same for the 83rd word, the 113th word, and the 25th word. And then I would take the average from that. So it's the same thing we did. The only difference is that we're allowing a calculator to allow us to do a truly random sample of the 5 words, rather than us picking the 5 words. Okay. So what do you think would happen if we had everybody in our class do this, come up with 5 different random numbers, and then calculate the average, right? What do you think would happen? Well, this is what actually happens when a class does that. We get this result instead, right? So here's the result when the students pick the words, and we had a median up here above 8. And when we let randomness pick the numbers, we had a median down here around 5. Interesting result, right? That we got a very different number if humans picked versus the random process picked, all right? And, the reason why that happens is because, humans are subject to our own internal biases, right? If you're picking what you think are 5 typical words, usually people don't pick the word like this single letter word here, right? Or I. They usually try to pick what they think are kind of the medium letter words that jump out at them. And so what happens is humans tend to pick the longer words. Just, it's an internal bias that you can't get around. Right? So every time I've done this in my class, there's always been a difference between the mean or the median between the student selected words and the randomly selected words. And the randomly selected words are always lower because they include a few of the smaller words that students never pick. Right? So that's the first thing, right? But even with the random process, there's still quite a bit of variation. Anywhere from average of 2.5 to average of 8. Average word length here, right? So quite a bit of variation, right? Now, that variation is referred to as natural sampling variation or random sampling variation. This is a phrase that we're going to see throughout the rest of the course. Random sampling variation, natural sampling variation. It just means that if you take a sample over and over again, even from the same population, then you're going to get different things every time you do that. That's totally normal, totally natural, right? Okay, so is there some way we could reduce this variation? Because the problem is that even though I'm going to have to pick a number for this, like maybe 5, right? That doesn't necessarily mean that's what I would get every time. So it would be better if somehow I could reduce this number, right? So usually what I have people do is say, okay, instead of taking 5 words at a time and finding the average, what if we upped it to 20 words or 50 words, something like that? And then we do this over again, where I have each student or each group of students run this and do, let's say, instead of taking 5 words at a time, we do 20 words at a time. And then we actually are adding up the numbers of letters in 20 different words from the chart. Right now, that takes longer to do, but when you do it, and then you find your average, and then you have a group come together. I'm going to show you the result from this other teacher. Now, this other teacher had them do 50 words. That usually takes a little too long. But you notice something, right? When we average 50 things, there's a lot less natural sampling variation, right? And it makes sense, right? Because for you to have something like 2.5 with only 5 words, it means a lot of those words were really small words, right? Same thing if you have 8, that means a whole lot of the words were really long words, 8 letters or more, right? But if you have 50 words, or if you have 20 words even, right, it gets harder to have 2 here, because then not just 5 words would have to be around 2, but 50 words would have to be around 2, which is very, very unlikely to happen, right? And so you start moving closer and closer to the true mean. In fact, later we're going to be able to show and prove that the mean of this sampling distribution, as you allow the sample size to increase, take more words to average, it gets closer and closer. This variation gets smaller and smaller until finally this is centered around the actual average if you were to do all 130. In fact, if you took a sample size of 130, then every single dot, every student would get exactly the same average, because it would be the true average of the entire population of words. Okay? So the second thing to note is that when you take larger samples, you have less natural variation from sample to sample. That fact is going to be really, really, really important later in the course. All right, let's go back to the notes then, and I want to show you a couple things further, and then we're going to talk about how we can use randomness. So the point of that Federalist paper is, number one, you can't trust your own human intuition, right? Can't trust humans to produce random results. Right? We are too biased. We have too many biases in our. And then the second thing is, as the sample size goes up, the natural variation, natural sampling variation goes down. Okay, my tablet here is acting up, so I'm going to close and reopen my papers here, but I'm going to continue rolling on the video. Okay, real quick here. Okay, let's continue with the notes here, because we want to talk about, now that we understand that randomness is important in order to avoid human biases, we can take advantage of processes like your calculator's random number generator in order to use randomness. Okay, so here's another example of why we don't want to trust our human intuition. If you show these two pictures to people, let me see, I make sure that I'm still on the, yep. Then which one would you say is random? Most people pick B because the dots are spread out, but actually that's incorrect. This is not the most random one. This is more random. This is truly random. This is generated by a random process. And what happens in random processes is that you have little clusters and groups of things, and you have spaces in there, right? So if you're, say, picking random numbers, a human wouldn't say that if you had a random number sequence that you had 1, 5, 4, 4, 4, 4, 4, 3, 1, 7, right? But in truth, real randomness does have patterns of numbers that humans tend to avoid. So all of this just basically to say that, you know, you can't rely on humans to produce results that are random, right? If you want randomness, then you have to do things like this. Like maybe you could write out identical pieces of paper with different choices, put them in a box, mix them thoroughly, and then randomly select some of the papers. Now that is a really random process. Or you could use dice rolls with a fair dice. Or you could use a calculator's random data functions, right? You can also use spinners, right? Or you can use a random digit table, which I'm going to show you how to use later. Okay, so we have to use some kind of a process to get true randomness. All right, so the next thing we're going to talk about is we're going to use this thing called a random digit table to do a simulation. So let's talk about random digit tables. At the back of our textbook and posted on the website, I've got a page from the textbook which contains numbers from a random digit table. And a random digit table, they just have numbers kind of grouped in 5, so it's easy to locate positions, right? But all these are just random sequences of single digit numbers from 0 to 9, okay? You have to use some kind of a truly random process to generate them. They're very difficult to create, actually. A typical way they're created is they will take, say, a radioactive element, and then they'll have a counter connected to a radioactive particle detector. And so whenever a particle is ejected randomly at a certain time from the radioactive particle, or the radioactive element, they start a timer, and then they measure the amount of time in, say, milliseconds until the next time that a particle is ejected. And maybe it's 23.017453 milliseconds, something like that, right? And then they say, okay, I'm just going to take the 4th digit, and that's the digit I'm going to put in the table. And then they let it go for a longer period of time, and the next one happened to be, 17.071552, and so they take the 4th digit, which happens to be a 5. So they use processes in the natural world that are known to be truly random. Okay, and then they analyze the data. They take all of this data and they take the data itself and look at it and make sure that if they do a histogram, that all the values are the same. There's not more of one value than the other. And then they look at every other one and they make sure that there's no pattern there. And they look at every third and every fourth and every fifth, and they make sure that it's truly random, right? So somebody has gone to all that trouble and produced a table that we can use. Okay, so I'm going to show you how we can use that to do a simulation. And we already talked about how we can use the calculator too. So the calculator has a random digit table built in. You seed it, by entering some random position to start, say, at that location, and then it just starts ticking numbers off of the random table from that point on to give you your random numbers, right? And to access that, if you want all numbers to be equally likely, you can use random integer. If you do, like, say, 0,9, it will produce random single digits from 0 to 9. If you add on a third variable there, then it produces an array with that many numbers, right? You can even do stuff like this. You can say random integer from 0 to 99, 100, and then press the store key and store that into a list. And then it'll load a list with all 100 values randomly selected between 0 and 99. And you don't have to necessarily make it so that all the values are equally likely. You can select the numbers from a normal distribution with a specified mean and standard deviation. You specify the mean and the standard deviation, and then you select 100 numbers out of that and load that, say, into a list, right? Then that's going to give more numbers near the mean and less that are farther away according to the probability of a bell curve, right? All right. But you do have to seed your calculator so that your calculator starts out. You just have to do that once every time you clear memory. All right, so let's talk about simulations. This is the second topic. The first one is just randomness in general. Now we're going to talk about how you use randomness to do interesting things. So let's consider this scenario. Let's say a cereal manufacturer puts pictures of famous athletes on cards and boxes of cereal. Okay, 20% of the boxes contain Tiger Woods cards, 30% contain Lance Armstrong cards. This is prior to his issues with, things that he got in trouble for. And then the rest of the cards are Serena Williams. So we have Tiger Woods, Lance Armstrong, Serena Williams. If you want to collect all 3 of the cards, how many boxes of cereal would you expect to have to buy in order to get the 3 cards, right? Now, that's going to change, right? You might luck out. You might buy the first cereal box and get Tiger Woods, and the second box has Lance Armstrong, and the third one has Serena Williams, or you're done, just 3, right? But you might buy like 5 boxes that all have Serena Williams and have to go all the way to the 13th box before you finally get the Tiger Woods card. And then the 15th box contains the Lance Armstrong card, and it took you 15 boxes this time, right? So one way to answer this question would be to actually go out and buy hundreds of boxes of cereal and try this over and over and over again to get a dot plot like we did, and then figure out the mean or the median of that. right? But that's really expensive and time consuming to have to buy and then open up all these boxes. So instead, we're just going to simulate buying a large number of boxes of cereal. Okay, so here's how we'll do that. And first, we're going to define some terms. So a simulation is just a sequence of random outcomes that somehow are modeling a situation. So in this case, the simulation is we're simulating buying a number of random cereal boxes. Okay, a component is the most basic event in the simulation. So in this case, the component is the selection of a particular box of cereal and then opening up to see what the card is inside. And then every time I do a component, right, I can get an outcome. And in this case, the possible outcomes are that the card is a Tiger Woods card or a Lance Armstrong card or a Serena card. Okay. So then I'm going to have to create some sort of a model that shows how likely these different outcomes are to occur. And then in that model, I'm going to show how there's a linkage between the outcomes and some sort of random process that I can use to simulate the outcomes. And then we're going to run one or more trials where we run the component until we've gathered all the data we need to answer the question, which in this case is we keep running, we keep opening boxes until we've achieved at least one of each type of card, right? And then we're keeping track of something as the response variable, the thing that's going to help us answer the question. So in this case, it would be how many boxes do we have to open in order to get one of each card? Okay, so the first thing is we identify the component, right? That's going to be a selection of a box of cereal so we can see what card is inside. And then we're going to create the model. Okay, so if you look at it, we said that 20% of the boxes have Tiger Woods cards. The problem said this, 30% have the Lance Armstrong cards, right? And then 50% have the Serena cards, right? So that means we have to use some kind of random process that connects random outcomes to the outcomes Tiger, Lance, and Serena. Okay, so I'm going to use T to represent Tiger, and L to represent Lance Armstrong cards, and S to represent Serena. Right, and these are actually just percentages, right? 20%, 30%, 50% that are adding up, right? But if I just use the digits 0 through 9, so I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that means that there are 10 different possible outcomes here, right? Right, and so every one of these represents 10%, right? So what I could do is I could just dedicate 10% or 20% of these outcomes, which would be 2 of the numbers, to represent getting a Tiger Woods card. 30% of the time I have to get Lance Armstrong. So I'm just going to pick 2, 3, and 4 here. That's 3 out of 10 or 30% are Lance Armstrong. And then the numbers 5, 6, 7, 8, and 9, 5 out of the 10, these represent Serena Williams cards. Okay, it doesn't matter which numbers you assign, as long as these represent 20% of the outcomes, these represent 30% of the outcomes, and these represent 50% of the outcomes. Okay. Okay, so then we're going to explain how we'll simulate the trial. So what we're going to do is we're going to keep opening boxes until we have at least one T, one L, and one S card, and we'll stop at that point. And then the response variable is how many boxes did we have to open, and then we'll run some trials. So typically, what you do is there's different ways you can do this. You could use your calculator to get these numbers, right? But let's actually use a single line from a random number table. So here's a line from a random number table. And we're going to do some trials here. We'll try to get 5 trials worth. Well, we'll just get as many trials as we can fit in this line. Okay. And every time I look at a number here, it represents opening a box, and the number tells me what kind of card we had. Let's remind ourselves that 0 and 1, those equal the Tiger Woods card. 2, 3, and 4 equal the Lance Armstrong card. And then 5, 6, 7, 8, and 9 represent the Serena Williams card. Okay, I really would like my thing to settle down here, but let me try it one more thing before we write this. Okay. Okay, so let's go ahead and do these trials. So I'm going to look at each of these numbers that represent a box, and I'm just going to write a letter above it, which represents what kind of card was in here. So 4, that means this box had a Lance Armstrong card. 0 was a Tiger Woods card, and 6 was a Serena Williams card. So right there, I've got all 3, right? And that means I can stop that trial, right? The outcomes were we had Lance, Tiger, and Serena. And the response variable that I'm keeping track of is how many boxes did I have to open? Well, I had to open 3 of those boxes. So the response variable was I had to open 3 boxes in order to complete the trial. Okay, so I'm going to move on to the next one. The next one is I have a Lance Armstrong card. That's a 0. That's Lance Armstrong. Nope, that's Tiger Woods. Sorry. That's a Tiger Woods card. 3 is a Lance Armstrong card. 1 is a Tiger Woods card. And then 6 is a Serena Williams card. Now at this point, I have at least one of every type of a card. So I'll end the trial there. This time my outcomes were Tiger Woods card, then Lance, then Tiger, then Serena, and it took 4 times to get the response variable. Okay, let's do another trial. Let's see, so 1 would be a Tiger Woods card, right? 5 is a Serena card. 2 is a Lance Armstrong card. So I have gotten my 3 cards. I got a Tiger one first, then a Serena Williams, then a Lance Armstrong card. It took 3 boxes that time. So you can see what's happening here. Rather than go out and buy a bunch of cereal boxes, you can simulate the trial, but you have to use randomness for it to actually represent what would have happened in the real world. Okay, let's do a 4th and a 5th trial. So 8 here is a Serena Williams card. 3 is a Lance Armstrong. 2 is a Lance Armstrong. 3 is a Lance Armstrong. 5 is a Serena card. Okay, 3 is a Lance Armstrong. 7 is Serena. 3 is Lance Armstrong. 6 is Serena. And then this 1 is the Tiger Woods card, and that finally completes the set. Right, so that time we had to go all the way through 10 trials, or sorry, 10 outcomes before we got the trial completed. So we had Serena and a Lance, 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 Serena, Lance, Serena, Lance, Serena, and then finally Tiger Woods, and it took 10 boxes to collect all the cards that time. All right, one more trial. We have 9, which is Serena, 8 is Serena, 7 is Serena, 8 is Serena, 3 is Lance Armstrong, 2 is Lance, 4 is Lance, 8 is Serena, 3 is Lance, 8 is Serena, 3 is Lance, 9 is Serena, 7 is Serena, 9 is Serena, 3 is Lance, 8 is Serena, and 0 is Tiger. Okay, so it finally took that long. We had to do 5, 10, let's see, 5, 10, 15, 17, right? We got Serena card, a Serena card, Serena, Serena, Lance, then a Lance, Lance, Serena, Lance, Serena, then Lance, Serena, 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 Lance, and then finally Serena and Tiger. So 5, 10, 15, 17 boxes had to be opened up in order to get the cards. Now that actually forms a distribution, right? I mean, if I were to graph it, I could say, here's 0 to 5, 10, 15. We could do a little dot plot if we wanted to. This is not a very big data set. We had two times it took 3, 1 time it took 4, 1 time it took 10, and 1 time it took 17. So I could start describing the distribution, right? Or maybe if I want to answer a question like, how many boxes would it take? Then you might report the median of these boxes, which would be 4. Typically it takes 4 boxes to get all the cards, but it can take as much as 17 in the experience that we've had. And of course, if you wanted this to be more robust, you might run 500 trials, right? Maybe program a computer to run a whole bunch of them and then see, okay, what's the real, the median? And then you could feel more comfortable in the range that it would take. All right, so state the conclusion. With the small number of trials, right, we might say we have to expect a median of 4 boxes, or a mean of 7.4 boxes, or you might even say as many as 17 boxes, because we saw it take that in one of our simulated trials. Okay, so the point is that you can use randomness to create a fake data set, but a data set which nonetheless represents the real world. And so it's valid to analyze that, to analyze the situation. All right, so that's everything in chapter 11. In chapters 12 and 13, we'll talk about how do you collect data from the real world instead of simulating it. But first, we wanted to talk about randomness and how to use it directly to create data sets.